Okay, I'm going to do an example now. This is on page 16, uh, volume 5. It's number 33.44. Give me just a second. All right, and so this is a lot like the example I was talking about. I kind of rearranged it so it would fit better on the whiteboard, and we're going to label things slightly differently now. I'm going to use theta 1 is going to be the incident angle for mirror 1, and I'm going to call theta 1 prime the reflected angle off mirror 1, just so I can fit things on the screen a little bit better. All right. And now I'm going to, I've got a protractor here, so I could try to do a little bit better this time. And I just want I want to emphasize that it's important to do these problems algebraically without numbers, and that's how we're going to work it out. But then we've also got the numbers that we can check things at the end. So I don't know if you can see this protractor very well, but this is about a 67-degree angle. This is 60, this is 70. It's closer to 70 than it is to, it's about halfway between there, maybe a little closer to 70. So I hope you believe me that that's about 67 degrees. And then right here, this angle is about 117 or 116, somewhere in there. What did I say? Which matches approximately the numbers I used in the book. So this is about as good as I'm going to be able to get it. And then let's trace the incident ray. Or the incoming ray as it goes through. We're going to use the one law we know, angle of incidence equals angle of reflection. So this one should spit out here. Let me just do it this way so I don't screw it up. I don't know. At about 67, it should go over and eventually hit this other mirror. And now I can't really, I don't want to measure the angles and try and do things that way. I'm going to do some calculations in a minute. And let me see here. Let's see, that should be about the normal for mirror 2. I guess I could eyeball this. Okay, somewhere in there. Whatever, I'm just going to eyeball it and draw it. Oh, I suppose I should measure and be a good person. Let's see, so that's about to 40. That should be about to 40. Right there, right there. This is just the best I can do with the space I've got. So there's our outbound or outgoing ray. Let me make sure that's on the screen. All right, so there's our outgoing ray. All right, and one of the things that I want to learn about is the angle between the incident ray. I've got a meter stick here, it's a little bit longer. This will help me. This is the incident ray direction. I don't know where it's going to intersect, so I'm going to make this extra long just in case. This is the direction of the incident ray. Now this one up here, can I get it just barely? I can't. Is the outgoing ray. And I want to point out something here. The ray bounces off these two mirrors and it's bent by this much effectively, right? So this is the angle, I called that beta. So our goal in this problem is to figure out beta, the angle between the incident direction and the outgoing direction. So notice I had to, what we say, back extend the reflected outgoing ray so that I could get this angle, right? But you could imagine this one was coming in and it's going to be bounced out that way. So it's effectively bounced off at this angle beta. So part A, Let me get, oops, there's my marker lit. I want to learn, oh, and so let's label some angles here. This should be theta one reflected, which I'm going to call theta one prime. Now I want to label theta two, the incident angle for mirror two. Think, it's to the normal, not this angle here. We're trying to use it. So this is theta two, and I'm going to call this theta two prime. So this is kind of a handy notation to use, where the reflected ray is always a prime and the incident, and so you'll see this in some textbooks instead of using subscripts I and R. They're both good styles. All right. So now in this case, I want to learn on part A, the question is determine theta 2 prime. Okay, well, let's work backwards from that. In order to figure out theta 2 prime, if I could just figure out theta 2, I could do this. Well, how am I going to do that? What do I know? What is given in the problem? We're going to assume theta 1 is given. All right? It doesn't say that in the problem right now, but I'll fix that when I get home. So given theta 1, and let's assume phi is given. So if we know theta 1 and phi, we can figure this out. All right, those are our knowns. We want to figure out theta 2. So we're like, okay, I know theta 1, I know theta 1 prime, because theta 1 equals theta 1 prime. Angle of incidence equals angle reflected. I know that this angle right here is 90 degrees. So I bet you I could figure out this angle. In fact, we know that's 90 degrees minus theta 1 prime, which is theta 1. Okay, so wait a minute. Isn't this angle right here related to that as well? Let's see. This is a right angle right here. So isn't this angle 90 degrees minus theta 2? Whoops, minus theta 2. So, I see that I know theta 1, I know phi, I should be able to get theta 2 and work my way to theta 2 prime if I use triangles. So let's go ahead and do that. I'm going to look at this big triangle up here, and I'm going to lightly shade this just so you can see it. It'll be fun erasing this afterwards. So I'm going to use this big red triangle right here. Is that showing up at all? Yeah, okay, cool. So let's use that triangle. And what do we know about the sum of interior angles of a triangle? I know they add up to 180. So I see that 90 degrees minus theta 1 plus 90 degrees minus theta 2 plus phi is all equal to 180 degrees. We're going to use this a lot, so it's good to know the sum of the interior angles add up to 180. All right. Well, when I do this, I could cancel out 90 plus 90 equals 180. So I'm going to cancel those out really quick. And so now I could get phi 2. I'm going to move phi 2 to the other side. You could pause the video, do the algebra real quick. I'm going to go ahead and proceed. So unpause now or whatever. Theta 2 is equal to, when I move this over, let's see, I get phi minus theta 1. So that's part, oh, and then this isn't technically phi 2 prime, but because angle of incidence equals angle reflected, I could then say phi 2 prime equals, theta 2 prime equals theta 2 equals phi minus theta 1. All right, so there is the outgoing rays angle to the normal. That's part A. Part B, determine the angle between, basically determine beta, between the incident and the outgoing. If you want to pause the video, now's the time. See if you have an idea of how to get there. All right. You can go ahead and unpause now if you want. All right. And what I'm going to do is I'm going to maybe work with this triangle here. I'm going to try and work with that angle. All right. And so let's see if we can figure out anything from this. There's a lot of geometry going on here. So this is good practice. If you, again, maybe you want to pause the video. Now that I gave you this hint that we're going to use this big triangle, you could use it. I'm going to go ahead and proceed. So in this case, I know that this angle and this angle must sum to 180. So this angle right here is going to be 180 degrees. Whoa. 180 degrees minus beta. Now, what about these angles in here? Well, take a look at this. There's lots of different ways you could think about this, but I know that this angle is 90 degrees minus theta 1, and I know that this angle here and this angle right here must match. So this is also 90 degrees minus theta 1. The 1 kind of got erased there, so I'm going to put that back in. So again, we use angle of incidence equals angle of reflection. Then these two angles add up to 90 degrees, which gave me this one as 90 minus theta 1. I used some kind of vertex angle here. And then similarly, you could guess that, well, if this is theta 2, this is theta 2, this is 90 minus theta 2. So this angle in here is 90 minus theta 2. Don't forget that degree symbol. So now we've got this jumbo blue triangle that we could use, and right, theta 1 is known, theta 2 we figured out in the previous problem. In theory, we should be able to figure out beta in terms of both phi and the given theta 1. So in this case, let's crank that out. I see that 2 times 90 minus theta 1 plus 2 times 90 minus theta 2 plus 180 minus beta equals 180. Give me a second. Make sure that shows up. How am I figuring that out? This is 2 times 90 minus theta 1. That's the first angle in this big blue triangle. 2 times 90 minus theta 2 is this one. And then here, this angle we got from supplementary angles, 180 minus beta. So these three angles, 1, 2, 3, have to add up to 180. And now from there, you could rearrange this and do some work. I'll let you do the algebra, but I've got the answer on the screen, so I'm going to cheat and get this video over with. You should be able to find that beta is equal to 360 degrees minus 2 phi. The fun part about this is, what angle do we need to retro reflect a beam, to point the beam straight back? Well, if beta is equal to 180 degrees, the beam's going straight back, right? So in this case, I don't use an angle of 180 degrees. If beta is equal to 180 degrees, phi must equal 90 degrees. And I've got that case right here. The idea is, if you take a mirror, two mirrors, and you bend it at 90 degrees, hopefully the light rays will go in and bounce off the next one and go straight back. And if you're trying to do this in 3 dimensions, just a sec. That's why these 3 mirrors are mounted at 90 degrees to each other. And so hopefully what happens is, no matter what angle you use for a laser beam coming into this, it should always go straight back, because, right, it's going to reflect off all 3. And as a result, it's going to come, well, all right, 3 dimensions a little bit harder. Let's leave it at that and stop this video. If you want to do the math, go ahead and do it. Look up retro reflector. Throw one of those things on the moon. You can shine a laser.